You clicked because you want to build your own version of Claude Code. You think it is just a few lines of code and a prompt. But the reality is that the magic you see is mostly a sophisticated orchestration loop hiding deep complexity. By the end of this video, you will understand why a simple loop cannot replicate the intelligence of the original system and where the true fragility of agentic architectures actually lives. The temptation is to treat tools like Claude Code as black boxes. You run them, they produce code, and you ship. But if you want to engineer the system behind the curtain, you must distinguish between the model's learned agency and the harness that enables it. Evidence from multiple open-source projects confirms that true agentic behavior does not come from handcrafted rules. It emerges from training on action sequence data. When you strip away the proprietary polish, you find that the core loop of perception, reasoning, and action can be replicated with minimal code. Yet, this replication reveals a critical trade-off that most tutorials ignore. Consider the architecture of a system built from scratch. Projects like the one by Windy 3F3F3F show that a 4,000-line implementation can capture the basic mechanics. You can create a React loop where the model thinks, acts, and observes. You can implement parallel tool execution to run commands simultaneously. But here is the thing. While you can build the mechanism, you cannot easily build the intelligence. The core bottleneck for coding agents is not the LLM's reasoning capability. It is the deterministic parsing of tool outputs and the ability to self-correct when the model hallucinates file paths or command syntax. This is where the gap between educational prototypes and industrial reliability becomes stark. A nano version of an agent might generate a simple snake game or manage a few files without issue. But when you push it to complex tasks, the lack of robust error recovery and cost control mechanisms becomes apparent. Without the proprietary optimizations found in the original system, custom agents struggle with semantic memory retrieval and state consistency. The context window becomes a fragile vessel. When you hit limits, the agent loses its train of thought, and the entire operation can collapse. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. You might think that simply coding a loop creates an agent, but the repository authors themselves note that complex behaviors require billions of gradient updates, not just architectural scaffolding. The reliance on external APIs for backends introduces latency and cost variables that challenge the notion of a self-contained, efficient agent. Every time the model makes a mistake, you pay for the token usage. Every time it loops, you waste time. The system requires explicit error handling logic rather than just prompt engineering to survive the chaos of real-world development. Now consider the safety implications. Building the agent harness from scratch gives you full visibility into failure modes, but it also removes the implicit guardrails of the proprietary version. This leads to significantly higher rates of infinite loops and destructive file operations in uncontrolled environments. When you strip away the proprietary polish, you see the raw decision tree. The humility reported by builders stems from the realization that current agentic architectures are brittle under ambiguity. They excel at well-defined tasks, but fail catastrophically when requirements shift mid-execution. This creates a profound understanding gap. Teams using the black box version often lose ownership of their codebase. The agent's autonomous refactoring creates complex dependency graphs that the original builders cannot trace without the underlying agent logic. When the black box makes a mistake, you are left guessing. When you build the system yourself, you see exactly where the logic broke. You see the moment the model hallucinated a path that did not exist. You see the retry logic fail because the error message was ambiguous. This visibility is the true value of engineering the system from scratch. The fragility of agentic state when context limits are hit is the most revealing insight of all. You might think the model is smart enough to remember everything, but in reality, the context window is a finite resource. As the conversation grows, the model must discard older information. If it discards the wrong piece of context, the agent loses its way. It starts making decisions based on incomplete information. The loop continues, but the quality degrades. This is not a failure of the model's intelligence. It is a failure of the orchestration to manage the state effectively. To truly understand the limits of current agentic architectures, you must look beyond the code. You must look at the training data. The ability to navigate complex code bases, to understand the nuances of a specific project, and to recover from subtle errors is baked into the weights of the model through massive training runs. No amount of clever prompting or loop design can replicate that depth of understanding. The mechanism you build is a vessel, but the intelligence comes from the training. This is the hard truth that separates a toy project from a production-grade system. So, can you engineer the mechanism of a coding agent? Absolutely. You can build a loop that reads files, writes code, and runs tests. Can you fully replicate the nuanced decision-making of the original without access to its specific weights and fine-tuning data? No. The gap between the two is not just a matter of lines of code. It is a matter of billions of gradient updates that teach the model how to think like a developer. The system you build will work, but it will be fragile. It will require constant supervision. It will break in ways you did not anticipate. This realization changes how you approach the technology. You stop treating it as magic and start treating it as a complex system with specific failure modes. You learn to design for the edge cases. You build better error handling. You accept that the model is not infallible. And you realize that the true power of these systems lies not in the automation itself, but in the human oversight that guides it when the automation falters. The future of software engineering is not about replacing the engineer. It is about giving the engineer a powerful, albeit imperfect, partner that requires a deep understanding of how to keep it on track. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.